Let's begin with a few definitions. Our first definition is a point. A point just represents a single location in space, like this, and often if we're representing points, we will label it with a capital letter, so this is point A. Next is the idea of a line. And a key aspect about lines is that in order to understand where the line is passing through, all we have to know is 2 points on the line. So for instance, the line that passes through AB can be drawn like this. And if we were representing this in standard notation, we would express it as the line AB. So we have capital A, capital B, and then a line above it to represent that this is representing the line. Our next definition is the definition of a plane. When considering a plane, think about a flat surface that continues outwards in all directions. Now maybe to help us visualize this a little bit better, imagine that you're sitting at a desk. It is a flat surface that has a beginning and ending we can trace along the edges of the desk. But imagine that that desk would then extend flatly outwards in all directions without end. That is the idea of a plane. Now keep in mind, to understand a line, we had to know 2 points, and then there's a similar relationship between planes. In order to identify a plane, we need to know 3 points on the plane. Because a plane can be represented by 3 points in the plane, we often use notation of 3 capital letters to represent a plane. Let's draw an example of a plane below. So here I've drawn a representation of the plane that goes through these 3 points, and while it seems like there's an end or corners, we know by the definition of plane, since these extend outwards forever, these would continue out in this direction forever and ever. Our next definition is that of a ray. A ray has a starting point and then a line continuing outwards in some direction, always in that direction. So there is a fixed beginning point, but there's no ending point because it will continue out in this direction forever and ever. So this is an example of a ray that's labeled CB. C is the starting point, and then it continues out passing through point B, and then will continue in that direction. Our next definition is that of a line segment. In a line segment, we have a beginning point and end point. So if we're asked to draw line segment AB, if we have point A and we have point B, then the line segment will just be the line that joins A to B, and it will start at A and it will stop at B. Now an angle is just 2 rays that have a common endpoint. So for example, we could have an angle that looks like, and then we can also measure what's called the degree of the angle, which is how far apart the rays are. So an angle with larger degree would look like, so here we have our 2 rays and the common endpoint. Now based on the degree of the angle, how far spread apart the rays are, we will label the angle as either acute, right angle, or an obtuse angle. So the definition of our first one, an acute angle, is an angle whose degree measures between 0 degrees and 90 degrees. A right angle is an angle that measures exactly 90 degrees. And an obtuse angle is an angle that is more than 90 but less than 180. Now let's describe the right angle in a picture format, and then after that I'll have a few angles listed and you try to classify whether they're obtuse or acute. So a right angle is exactly 90 degrees, and in order to show that the angle is exactly 90 degrees, often we will see this little box in the middle. That indicates that this is an exactly 90-degree angle. Now where have you commonly seen 90-degree angles? Well, often if you look at where your floor and walls join, those should be 90 degrees. We also might hear the phrase perpendicular. So we're used to 90-degree angles in our house, and if it's less than 90 degrees, so that means the angle is less than that, so maybe something like this, that's an acute angle. And as we look, the obtuse angle is that which is greater than 90 degrees but less than 180. So to be greater than 90 degrees, we might share this same one, but then it goes even farther past. This would be an example of an obtuse angle. So of the angles listed A, B, C, and D, take a moment to think how you would classify each of these. Are they acute angles or are they obtuse angles? Angle B and C are acute angles, and angle A and D are obtuse angles. Let's draw these angles underneath the definition so we have these as a reference in our notes. Now let's consider what would an angle look like if it measured 180 degrees. Well, we know what a 90-degree angle looks like. That's like our right angles. We know an obtuse angle is more than 90 but less than 180. So let's imagine what would happen if we added two 90-degree angles, because 90 plus 90 is 180. So if we have one 90-degree angle, and then let's draw another 90-degree angle towards the other direction, we see I have a 90-degree angle plus another 90-degree angle. So altogether, we'd get a 180-degree angle. So a 180-degree angle looks like a horizontal line. If we have two lines intersecting, and if they intersect in right angles or measuring 90 degrees, then they would be called perpendicular lines. Here we have our first line shown in blue, our next line shown in red, and we'll know that they intersect to be right angles if you see one of the four angles shown to be this 90 degrees, because in fact, if one of the angles is 90 degrees, all of them are 90 degrees. We just often write only one of them for ease of notation. So this is a special case when lines intersect at exactly 90 degrees when they're perpendicular. But lines could intersect at other angle measures as well. When any two lines intersect, we have the idea of opposite, also known as vertical angles. The meaning of opposite or vertical angles is that angles directly across from each other in an intersection of two lines are equal in value. So these two angles that I've shaded here in pink are the same value. Similarly, the two angles that are shown in tan with the double lines to differentiate the difference between the first one are equal to each other. Now we're going to use this information in later problems where we're given information about some of the angle measures in intersecting lines and we're asked to find the other. So keep in mind the idea of opposite angles. Angles that are directly across from each other are equal. Keeping this idea in mind, let's think about how we could solve this example. Here we see that I have two intersecting lines, line 1, line 2, and we're asked to find the value of x. Now, x itself is only mentioned in the problem in that they tell us the angle measure that I'm showing here in pink is equal to 4x minus 5, and the angle measure that I'm showing in green is x plus 16. However, keep in mind that as these are opposite angles, they're directly across from each other, we know that they're equal, and that means I can set up the equation whatever x plus 16 is, it needs to be equal to 4x minus 5. So what we used here is the idea of opposite angles allowed us to realize these are the same thing. Now that we have the equation, it's just algebra to solve for x. I'd encourage you to pause the video at this moment and solve this using algebra. Unpause to check your work. So we'll subtract x from both sides. 16 equals 3x minus 5, add 5 to both sides. We have 21 equals 3x, divide both sides by 3, type this into our calculator, and we'll get x is equal to 7. So that's the value of x, and although this problem didn't ask for it, if we were asked to find the measurement of the angle, I would either have to say 4 times 7 minus 5 or 7 plus 16. Either of those would get me the angle measure. But here we can stop as we were just asked for x. So in this next example, we're asked to solve for y. This is similar to our last example. I'd encourage you to take a moment and pause the video, attempt it on your own, unpause to check your work. So as we're looking at this problem, we see that I have two intersecting lines, the first line here in blue, the second line here in tan, and as they intersect, we know that angles directly across from each other are equal. That's our idea of opposite or vertical angles. Specifically, these angles are across from each other, so I can mark that these two angles are equal. So one single angle marked with one single angle, that's notation that these are equal. If I want to show that these across from each other horizontally are equal, but not necessarily the same, I would use the double angle mark notation to differentiate and say both of these are equal, but they're not necessarily the same as what we see in the red ones. So from opposite angles, we know 9y plus 7 must be equal to 2y plus 98, and then we can use algebra to get y by itself. So let's subtract 2y from both sides. We're left with 7y plus 7 is equal to 98. We'll subtract 7 from both sides. And we get 7y equals 91. Divide both sides by 7. And we'll find that y is equal to 13 when we type this into our calculator. So our next definition is that of complementary angles. Two angles are said to be complementary if when you add the two angles, you get exactly 90 degrees. Now, this could occur if we're told angles are complementary, then we know we add to get 90 degrees, or we could be visually told that angles are complementary. See in this first example, I have a 90-degree angle indicated by this little box in the corner. So I know this is a 90-degree angle, however, it's split into two smaller angles. The first part of the smaller angles is this angle x, and then added directly to that to make up the rest of the 90 degrees is this 62-degree angle. Since they're both part of the overall 90-degree angle, we know this must be a true equation. X plus 62 equals the overall 90 degrees. So with this, we can quickly find x by subtracting 62 from both sides. And we would find that x is 28. Now take a moment to look at our next example. Visualize why this is a problem related to complementary angle or angles that add up to be 90 degrees. So here we have a right angle or 90-degree angle as the largest angle, and itself is split into smaller angles. We see it has the smaller angle x minus 3, x minus 1, and x plus 1. All three of these together combine to be 90 degrees, so we could write out the equation x plus 3 plus x minus 1 plus x plus 1 is equal to 90 degrees. And this is because all three of these are subparts of an overall 90-degree angle. And now to get x by itself, we will combine like terms. X plus x is 3x's. 3 minus 1 plus 1 is exactly 3. That's what's equal to 90 degrees. And now we can solve to get x by itself. Let's subtract 3 from both sides. And when we do, we'll get 3x equals 87. Divide both sides by 3. And we'll find x is equal to 29 degrees. Now that's enough to finish this problem, but if we were asked one further step, if we were asked to find exactly the measurements of this angle, and this angle, we could do so knowing each x is 29, so the lowest angle, x plus 29, is 29 plus 1, which is 30. Next is x minus 1, which is 29 minus 1, which is 28. And then x plus 3 is 29 plus 3, which is 32. Add all those together, and we definitely see it adds up to be 90 degrees. A related idea to complementary angles is supplementary angles. Two angles are said to be supplementary if when you add them together, you get 180 degrees. And keep in mind, 180 degrees, that's our straight line angle. So a line is an angle of 180 degrees. Now we can see in the next two examples, we clearly have straight line angles of 180 degrees. So for the first one, it goes from point A to point C. However, that 180 degrees is transected. We see we have it split on the right side with the angle that's 65 and split on the left side with the angle that's x. Now altogether, both angles are part of the overall 180 degree angle. So whatever x is, if you add 65 to that, we know we have to get 180. Now just to reiterate, where am I getting this 180? Even though it wasn't mentioned at all in the problem, visually, as this portion is a straight line, we know a straight line has an angle of 180 degrees. So that's kind of implied because both of these angles make up a straight line angle. Now we can solve to get x by itself. We'll subtract 65 from both sides, and we'll get that x is equal to 115 degrees. Now before we attempt the next problem together, I would encourage you to pause the video and attempt this one on your own. Unpause to check your work. Now as we're looking through this problem, we see a straight line angle, and we know that a straight line angle is altogether 180 degrees. Now this straight line angle has been split into two portions. The first portion is angle x minus 6 combined with the portion that's 2x plus 3. Now altogether, these two portions added together we know must be equal to 180. So 2x plus 3, whatever angle that is, plus the angle x minus 6 must be equal to 180. And we're about to be able to solve the problem. We do know that we need to combine like terms. So we have that 2x's plus an x would be 3x, plus a 3 minus a 6 would be a negative 3. Now that is equal to 180. We can solve for x now. We will add 3 to both sides, which will get rid of the minus 3 on the left side. And when we do, we get 3x equals 183. 3 and the x are being multiplied, so to undo that, we'll do the opposite, which is divide. Divide both sides by 3. And if we type this into our calculator, we get x should be 61 degrees. Previous examples gave us pictures of angles, and based on the properties of the angles in the picture, we knew whether we were dealing with angles that added to be 90 or angles that added to be 180. Whereas in this example, we're given a verbal description, and based on the definitions, we need to figure out what is the information they're giving us and how can we work with it. So let's read through this together. If an angle measures 15 degrees less than twice its complement, what is the measure of the angle? Now I think the first key thing that we need to figure out is, what does the phrase its complement mean in this context? Now if we look back a little early in our notes, we see that complementary angles are angles that add to be 90 degrees. So that key phrase of twice its complement is related to the fact that both the angles will add to be 90 degrees. Now in this case, we're dealing with some unknown things. We know if we're dealing with a complement, there's two angles that add to be 90 degrees. We don't know the measurement of either angle. So when things are unknown, let's start to give some labels so that we can talk about it. The angle we're looking for is x. Its complement, so the possessive x's complement, let's call y. And now we need to translate this phrase into an equation. So x measures, so x is the idea of equals, 15 less than twice its complement. Let's give everybody a moment. Write down what you think might be a correct equation in this case. So as I'm working through this, we're thinking twice its complement means I'm going to multiply y by 2. 15 less than this means take 15 away from this value. That's what x measures to be. So x is equal to 2y minus 15. And if we were to draw a picture of this, we see that I have my 90-degree angle split, and we have x and y. it turns out x is 2y minus 15 based on the verbal description in the first sentence. Now we know, added together, this entire angle is 90 degrees. So y plus x equals 90 degrees. And if we just leave it like this, we're kind of at a loss of what to do next because we're not used to solving problems in multiple variables. However, if we go back to earlier parts of the problem, I think we'll be able to get some traction. X is 2y minus 15. So instead of leaving this term as x, which is not particularly helpful because it leaves me with multiple variables, what if I substitute its equivalent value of 2y minus 15? So we'll do that above here. So we have that y plus 2y minus 15 is equal to 90 degrees. Now we can combine like terms y plus 2y. That combines to be 3y minus 15 equals 90 degrees. And at this point, we can solve to get y by itself. Once we know what y is, we can find what x is because 2y's minus 15 is equal to x. So let's isolate and get y by itself. We can do so by adding 15 to both sides. We get 3 times y is 105. Divide both sides by 3 because that's the opposite of multiplication. And we'll get y should be equal to 35. So this angle here is 35 degrees. Now we know 35 plus the unknown is 90. Said another way, 90 minus 35 is the unknown. Through that, we can figure out that the unknown angle is 55. Or alternatively, y is 35, but we know 2 times y minus 15 is x. So 2 times 35 minus 15 will be equal to our x value. Type this into our calculator. 70 minus 15 is equal to 55. So x is 55 degrees. One idea we need to carry forward is the idea that we previously talked about, opposite or vertical angles. That's the idea if two lines intersect, then the angles directly across from each other are equal in value. And then some more ideas about angles will deal with the intersections of three lines. In particular, if we are shown two parallel lines, and another line will cross through the parallel lines, that's what we see here in our red, the intersection of these three lines forms 8 different angles. Let's count the different angles. We have this first angle, angle 1, angle 2, angle 3, angle 4, angle 5, angle 6, angle 7, and angle 8. Through different properties, we will be able to see how the different angles relate to each other. Now we're about to learn the new ones, but let's just base it off of opposite angles. Based on what you know about opposite or vertical angles, which of these are equal to each other? We know that angles directly across from each other are equal, so for that reason we would say angle 1 is equal to angle 4. Similarly, angle 2 equals angle 3. Now think of the angles 5, 6, 7, 8, which are equal. Angle 6 and angle 7 are equal, and angle 5 and angle 8 are equal. So that's all based on our idea of opposite angles. Now based on this image of the three intersecting lines, which angles are supplementary angles? We have that angle 1 plus angle 2 would add to be 180. Similarly, angle 3 plus angle 4 is equal to 180. Now if we see it in a different direction, angle 1 plus angle 3 is also equal to 180 because they add up to be a line. And similarly, angle 2 and angle 4 also add to be 180. And there are similar relationships between angles 5, 6, 7, and 8. So what we've done so far is in this picture of the 8 different angles formed by the two parallel lines and then a line crossing through them is our ideas of opposite and supplementary angles. What can we figure out from those? Now let's learn a few more rules that will help us calculate even more relationships between the various angles. So our first rule is that of alternate interior angles. Now to help us keep sense of this, the phrase alternate means on opposite side of this transecting line. So notice angle 4 is on the right side, angle 4 is on the right, angle 5 is on the left, so they are on alternate sides of the transecting lines. And then the phrase interior means it's inside the parallel lines. So things inside the parallel lines are interior. So it turns out if you have two angles that are alternate the transecting lines, but interior the parallel lines, they are equal. So this is the notation for angle 4, the little angle symbol 4. Angle 4 equals angle 5 in this picture. Now our next rule is that of alternate exterior angles. So alternate means that it's on either side of the transecting line, which we see in this case. Angle 1 is to the left, angle 8 is to the right. But exterior means it's outside of the parallel lines. So these would be angles that are exterior. So alternate exterior angles are equal, so angle 1 equals angle 8. Now interior angles, so remember the phrase interior is the idea of inside the parallel lines. Interior angles on the same side of the transversal, so they're not alternate, they're on the same side, so they're interior but on the same side. They are not equal, but they do add to be 180. So angle 4 plus angle 6 is equal to 180 degrees. And our final rule that we're going to use is corresponding angles. So a corresponding angle is an angle in the exact same location, but just based on the other parallel line. So for instance, angle 2 is above the parallel line and to the right of the transversal. Similarly, angle 6 is above the lower parallel line and to the right of the transversal. So whenever you have the angle in the same location just on a different parallel line, those are corresponding angles and they are known to be equal. So angle 2 equals angle 6. So if we remember these four rules, the idea of complementary and supplementary angles and opposite angles, we will be able to find the missing angle measurements given just a little bit of information. So in this first example, we're asked to find the value of x. Let's zoom in here on the angles shown. So here I first recognize that I have my two parallel lines, A and B. And of the angles marked, I try to make sense of them. How are they related to each other? Where are they in relation to the parallel lines, to the transversal? So in this case, would y'all agree that both this angle and this angle are interior angles? They're inside the parallel lines. Additionally, they're alternate of each other because this is on the left side of the transversal, whereas this is on the right. So this is why we would give these the phrase alternate interior angles. And if we look back at our notes, we see that alternate interior angles are equal to each other. So we can set 3x plus 16, that's the angle measure here, is equal to 5. So after adding 54 to both sides, we see it cancels from the right side, and then we're left with 16 plus 54 is equal to 70, which is equal to 2x. To get x by itself, it's currently being multiplied, so we can divide both sides by 2. And we'll find that x is 35 degrees. Now in this next problem, we're asked to find y, and then from that, find all the different angle measures. Let's begin by finding y. How would you classify these two angles? The first thing we might note is that they are alternate the transversal, so we'd use the phrase alternate. Additionally, they're on the exterior of the parallel lines, so taking those two things together, we would call these alternate exterior angles. Now if we look back in our chart above, we see that alternate exterior angles are equal. So take a moment to write down what equation do we then know is true. If alternate exterior angles are equal, then 3y plus 53 must be equal to 7y minus 55. Now once we were able to set up this equation, once we realized that these are equal angles because they're alternate exterior, once the equation's set up, it's just algebra. So let's solve and get y by ourselves. We know that we could subtract 3y from both sides. When we do so, we're left with just a 53 on the left side equals 4y minus 55 on the right side. Now to get the y by itself, let's add the numbers to one side, so add 55 to both sides. And when we do, we get 108 equals 4 times y. To get y by itself, we'll divide both sides by 4. And we get that y is equal to 108 divided by 4, or 27 degrees. Now we were asked to find all of the angle measures, so keep in mind y is 27, but that does not mean this angle is 27. In fact, what we'll need to do here is substitute in 27 in for y, so 3 times 27 plus 53. And we see this angle should be 134. Now if this angle is 134, its alternate exterior is also 134. Now keeping this in mind, since we were asked to find all the angle measures, we also need to find the angle across from 134. How could we find this angle measure? Well, we know that together they make up a straight line, so that's 180. So 180 minus 134 will give us this missing angle measure, gives us 46. So this angle measure is 46. By same reasoning, this is 46. And then we have a particular name for angles that would give us this angle measure that is directly across. Remember, opposite angles are equal. So if this is angle 134, then this is angle 134. Similarly, if this is 46, then directly across is also 46. If this is 46 down below, then directly across is also 46. And directly across from 134 should also be 134 via our opposite angles. So now we've completed this problem. Not only did we find the value for y, but then using that, we were able to find all the angle measures from the intersection of these three lines. So that's all there is in this section of notes. As always, if you have questions, please reach out and I'll be happy to answer them.